Here we are glad to introduce our work towards embodied scene description. Let's start with the motivation of our work. Why do we move from scene description to embodied scene description? Recently, great progress has been made in the areas of image captioning, dense captioning, and image paragraphing. It has been becoming more and more mature with the booming of deep learning techniques. These tasks can be summarized as image-based scene descriptions. These scene description techniques are useful in practical scenarios. For example, Microsoft has developed an app named Seeing AI for visually impaired people to learn about their surroundings. Here are some amazing examples where the app is able to give accurate descriptions of an indoor scene. However, with improper viewpoint, poor description can be generated for indoor scenes. For example, when the camera is facing a corner of the room, it cannot give meaningful description of the room. The main problem here is that existing scene description tasks mainly focus on analyzing images passively, so the semantic understanding of the scenario is separated from the interaction between the agent and the environment. When the camera is facing a corner of the room, it's more useful to tell the user where to look next rather than just providing him the vague description of the current scene. This motivates us to propose a new problem of embodied scene description. It's an intuition demo of our proposed framework. At the beginning, the camera is facing the corner of the room, and the description generated is poor. We hope a model could tell the user to turn left, which gives a much better viewpoint. And then the captioning model can be used to generate a more accurate description of the room. We believe the proposed embodied scene description task can be widely applied to many different kinds of robots, such as military robots, education robots, or medical robots. It can also be used by general photographing systems, helping the camera find a better viewpoint to take photos. Now let's move on to the second part of this video, and we will formulate the problem of the embodied scene description. The robot navigates in the room, hoping to find a good location to describe the room. At first glance, the robot captures an image from an initial viewpoint. Since this image is not informative at all, the generated caption provides very limited information about the room. Then, the robot explores the room by itself and a better viewpoint is found to capture a new image. At this time, the generated caption gives more informative and suitable results. Then let's move on to the network architecture of our embodied scene description model. This is a network architecture at a single time step. The action the robot would take in one step can be relevant to all its previous actions and observations. Therefore, the LSTM network is used for this sequence modeling. The output of the network is the action the robot would take for the next step. With the learn policy, the agent is expected to take as few steps as possible to approach the target scene from a random starting position. This is a full network architecture with unrolled LSTM time steps. In the training phase, we use imitation learning to minimize the loss function between the generated action sequence and the ground truth action sequence. In the inference phase, the output action of each time step is used as the input of the next time step. This process iterates until the robot stops. In the following video, we will show some representative experimental results of our proposed method. Here is a successful example when applying our proposed framework to image captioning task. It's a bedroom in the simulator. Here are some more examples for different types of rooms. The proposed framework is also applied to dense captioning models, where text descriptions for each region of the image are generated. Here is a successful example when applying our proposed framework to dense captioning task. This is a living room in the simulator. Here are some more examples. The proposed framework is also applied to image paragraphing models, where a long paragraph is generated to describe an image. Here is a successful example when applying our proposed framework to image paragraphing task. This is a living room in a simulator. Here are some more examples. Sometimes our proposed framework will encounter failures in some scenarios. We will show some failure cases and analyze their causes. This is an example of failed scene captioning. The navigation model works fine in this example. Almost everything in the kitchen can be seen from the last frame. However, the image captioning model still gives a non-informative result. Such kind of failure is mainly caused by the limitation of current image captioning models. Here is a failure case for dense captioning task. The agent stops at a final viewpoint similar to the initial viewpoint. This kind of failure is mainly caused by the navigation model. Besides the experiments in the simulator, we also perform some experiments in the real-world scenarios. We will share some results in the following. In the real-world experiment, we use a caster, a commercial robotic platform, together with a Kinect sensor. In this example, the robot firstly faces to a corner of the room. With the generated instructions, the robot moves around the room until it recognizes that it is a bedroom. In this example, the robot starts with a position where it faces to the door of a cabinet and it is difficult to obtain much useful semantic description. Then, the robot adjusts its positions gradually and stops at a position where it can get a full view of the room. Here are the conclusions. In this work, we propose a new embodied scene description problem in which the robot exploits its embodiment ability to find an optimal viewpoint for scene description tasks. The trained model is evaluated in both a simulation and a real-world environment, demonstrating that the agent is able to actively explore the environment for good scene description. The embodied scene description will enable the visually impaired people as well as robots to understand the environment actively. Acknowledgement. The paper containing the technical details has been accepted by RSS 2020. This work was supported by the National Key R&D Program of China and National Natural Science Foundation Key Project. We acknowledge iQtint Robotics for providing the Castor platform for our real-world experimental validation. Thank you for watching.